Welcome back to our statistics learning session. Today, we'll be talking about p-value of one-sided test. For this, we have an example of a cookie. In this example, we have 32 cookies, 32 chocolate chip cookies, where each cookie have chocolate chips on them. Therefore, the 32 is our n. Let me highlight this. 32. This is our n. This is about exercise. Let me go through the our problem statement, and we will talk about it later. The question is, students are asked to count number of chocolate chips in 32 cookies for class activity. They found that the cookies were on average had 14.77 cookie chips with a standard deviation of 4.37 chocolate chips. The packaging of these cookies claims that there are at least 20 chocolate chips per cookie. One student thinks this number is unreasonably high since average they found is much lower. Another student claims the difference might be due to chance. What do you think? And also we need to compute the p-value for this. How should we go about it? Here, 32 is n, as I said before. Average, 14.147 is average, which is x n bar. And standard deviation is sigma, which is 4.37. So now you can imagine that students who were really busy studying were quite upset about this when they were eating chocolate chip cookies, and there were really few chocolate chips in the inside the cookies that advertised in the box. As we saw in the problem statement, some people thought there is a possibility that the low number of chips in cookie occurred because of variability. Now we have to answer our question: is this due to chance, or this is actually false advertising on the box? How should we go about it? To solve this problem, we have to create an experiment. And to create an experiment, we will start doing some modeling assumption. What are those modeling assumptions? The modeling assumption is that we need to assume that the number of cookies, number of chocolate chips are xi, chips in cookies. It is IID. It is IID variable. Xi is IID variable, which is number of chips in cookie. That's a modeling assumption. Another modeling assumption we want to make is xi is not only IID, it is a normal distribution, a normally distributed variable. That is mu and sigma square are these parameters. So it's a Gaussian variable. That's what I'm trying to say. And is it okay for us to assume it's Gaussian? Yes, it is, because we have 32 cookies. So 32 observations. So we have 32 cookies. Observation, and it is more than enough for us to assume it's Gaussian. To assume something is Gaussian, we need at least 30 observation, and it is we have 32 here, so it is more than enough. And since it is we are summing a bunch of independent stuff, there is occurrence of number of cookies in each, number of chips in each cookie, chocolate chips in each cookies, it is independent. Therefore, so we can use the Gaussian as our distribution. This is our model. Let me write our model. Our model is this. So this is our model. What is mu here? Mu is undefined. What is sigma square? Sigma square is 4.37 square, which is given in the problem statement. Now we have to write a test or create hypothesis. What are the hypotheses? The null hypothesis is that mu, it is a baseline statement, or that is it is a benchmark statement. That is mu is less or equal to 20. Mu is greater than or equal to 20. That's a statement given in the box. Our hypothesis is mu is less than 20. That's the alternate hypothesis that we want to prove. Now, I have a few questions for you. Is this one-sided or two-sided test? It is one-sided test or two-sided test. It is one-sided test, isn't it? Now, my second question is it one sample or two sample test? It is one sample test, isn't it? So this is my test, and here, and we have x n bar as 14.77. So let's start from the scratch. Let's assume that for our null hypothesis to be true, x n bar has to be smaller than something, some value. X n bar has to be less than some value. We don't know what this value is. Now we need to centralize. We need to normalize this variable x n bar by subtracting mu and dividing by the dividing by some value. Let me just quickly check what value is that here. Let me just quickly check what value is that here, because I forgot right now. That value seems to be sigma. One second. I'm sure I can find it out for you. We need to divide by sigma square. We need to divide by sigma square, which will give us some value. Now, we'll do further processing of this, which is equal to sigma mu sigma, which is less than some value. And what is this value? This value is q alpha minus q alpha. Correct? Isn't that right? Yes, it is right. Therefore, this is our test statistics. In another form, we can say that is greater than q alpha. Now, we could have used the student distribution instead of Gaussian distribution. But for this, we don't need to do that because Gaussian distribution and student distribution are same when the observation count of observation is more than 30. So we just went with the Gaussian distribution and there's no problem. Now, the question is what mu we should choose. The mu we should be choosing is the mu that is right at the boundary. And what mu is right at the boundary here? Can you tell? The mu that's right at the boundary is one that's in hypothesis we just generated. It's going to be 32. Xn bar, what's our Xn bar? Xn bar is 14.77 minus 30. And sigma is, what is our sigma? Sigma, the square root of 4.77 is how much? Let me calculate here. Square root of 4.37 is equal to, let me calculate again, square root 2.09. 2.09. That is, we have 30 minus 14.77 divided by 2.09 equal to 7.28 On top of that, we need to multiply it by square root of 32. That is 32 square root is 5.65 multiplied by that is 41.22. Is that right? Let me see. Let's step back for a while. Let me see if I'm doing it right here. Square root of 32. The answer we need to do is here square root of 32. Let me quickly check whether I'm doing it correctly. 4.37. That is sigma. We don't need to divide by 2.7. We don't need to do that. We need to just divide by 4.37. Now let's see how it goes. Let's try it again. 30 minus 0.77 divided by 4.37 multiplied by 30 square root equal to this is correct. This is 19.7 something. 19.71 something. Now question is is this greater than Q alpha? Let's see. What we have a Q alpha here. Let's take a look at our take a look at our standard normal distribution chart, and the maximum value of 0.998, the maximum value is 3.409, and we have 19 here, and we have 19 here. What I'm saying is that alpha xn mu is greater than Q alpha, and it is 90.71 this side and is greater than Q alpha. Q alpha Q alpha can be the value of Q alpha. Q alpha, which is actually a Z score, can be up to 3.49. That's the maximum positive value it can go up to. But this is 9.7 is far greater than 3.49. Since this is true, then our alternative hypothesis is true. The test has passed. That is, Tn is greater than that means sigma that means sigma is greater than 1. That is, test has passed. That is, alternate hypothesis has been approved. Therefore, we can reject the null hypothesis and move to our alternate hypothesis. So that's all for today. Let me quickly summarize what we learned today. We did some exercise today about cookies. Cookies that had chocolate chips on them, and there are 32 cookies. We model these 32 cookies as observation of the Gaussian distribution and use the observation to compute, to create a model and to compute a p-value out of the model and whether that p-value is a realistic. And using the same value, we looked whether we can reject a null hypothesis at any level. And from this, what we can see is that I can reject null hypothesis at 1%, 5%, 10%. No problem. I can reject null hypothesis 1%, 2%, 5%, no problem. Because this 19 is a way, way below, is even less than 1%. Therefore, we can reject the null hypothesis and go toward alternate hypothesis. Thank you. That's all for today. I'll see you next learning session. Thank you so much.